Hi, I'm Jesse. I'm an engineer at Cloudflare, and many of you here may know Cloudflare as CDN or DDoS protection, all those things. Actually, the Cloudflare dashboard is built in React as well. So we use a lot of React internally for that. So when you log in and change your DNS records or whatever, you're using a React application. So I'm going to start my talk by introducing, for those of you who aren't familiar with it, Conway's Game of Life. So it was invented in 1970 by a mathematician named John Conway, and it's sometimes described as a zero-player game. So you start with a square of a grid of cells, and each cell can have an initial state in which it's either alive or dead. And then there's a sequence of turns, and each turn, a cell can either die or come alive depending on the status of its cells around it. So the algorithm is really simple. If a square is alive and it has 2 or 3 neighbors that are also alive, it stays alive. Otherwise, it dies. If a cell is dead and it has exactly 3 neighbors, it becomes alive. Otherwise, it stays dead. So I wanted to write the worst application I possibly could. Something that would just perform terribly. And so I hit upon this idea. I'm going to try to implement a Conway's Game of Life in React. I'm going to have a 100 by 100 grid. Every cell in the grid is going to be a DOM node, so that's going to be 10,000 DOM nodes. And I'm going to update every DOM node every time a timer ticks and evolves the game of life. And I'm just going to try to make this a terrible application, and I kind of failed. So we're going to take a look at why. So first of all, I tried to break every rule of the, you go look at the performance recommendations for React, right? And it's got all these things that you're supposed to do. Long list of elements should have keys. Don't pass extraneous properties to your components, and maybe don't create enormous lists of 10,000 elements all within a single render call. So I did all of that stuff, and I learned a few things on the way about this. First of all, React is pretty fast, especially if you're using pure React without any other libraries or systems on top of it. The whole application that I wrote is about 250 lines. For reasons that will hopefully be clear to all of you by the end of this talk, this was actually a terrible application to try to demonstrate poor performance on. Uniform fields of shallow elements are incredibly fast to render, and it's actually hard to make them slow. And there were a couple of things that mattered far more than any code that I wrote about how to make things fast. First of all was to use a production build instead of a development build of React. And that was worth about 4x performance, 4x performance improvement. And then the other thing was the debugger makes a huge difference in the performance of your website. So I would be working on the website, and I'd be trying to make it slow, and so I'd do a de-optimization, and it would speed up. And then I would try again, I'd reload, and I'd do an optimization, and it would slow down. Close the debugger. And definitely don't have any breakpoints set, even if they're disabled. You cannot do performance testing that way. So I instrumented my app with a little timer. It starts at the onRender loop and records the time, and then it has a set callback with time 0. So it gets control again as soon as rendering stops, and so we measure the time. And so my little app, there it goes, took about 160 milliseconds to render each iteration for 10,000 DOM nodes. Not too bad or not too good, I guess, depending on your perspective of what was trying to be accomplished here. You definitely wouldn't want a 163 millisecond render cycle in your application, though, right? People type way faster than that. But in the end, almost all of the performance or lack thereof came down to one de-optimization, which we'll come back to towards the end of the talk. There we go. So let's go and do a reminder about React without JSX. So how many people have written a react.create component call, react.createElement call anytime since like the first day that they learned React? I see like a handful of hands. Oh, a few more than I was expecting. So JSX is really build time syntax for react.create component. There's a Babel component that goes through your code, and it looks for all the JSX and converts every JSX element to a react.create component call with the component and the children that are going to be called. So let's open up our command line and let's type yarn create react app. And we get an app that looks something like this. I deleted a couple of things for the sake of making it even shorter. This is what our app looks like in JSX. So now we take our heads and we run Babel in our heads, beep, 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 beep. And we get the same thing implemented as CreateElement calls. So a couple of things to notice about here. About this. The return call, the return value of CreateElement is an object called an element, and React documentation describes it as cheap and fast to create. This, like all other functions, is executed from the inside out. So CreateElement code gets executed first, and then that gets passed to CreateElement P, and so on up the chain from the bottom, essentially the bottom of the tree to the top. And what we're passing in are component props and children. And so in the end, once this call is evaluated, we have a tree of objects where we've got a root, and then there's object references to each of its children, and so on down the line. So you'll probably recognize this. What else is a directed acyclic graph? The DOM. This is a common way to represent DAGs in computer science in general, and especially in the world of the web. So the example we just looked at was React Create component called with just HTML elements. But what about our own components? Oops, that should say create element there. OK. So thing to notice here in big arrows is that there are no parentheses, right? Our Babel has compiled it, or we've written this, and we put in the unexecuted function or component, and React takes care of managing the lifecycle for us. So after we call this, if it's necessary, React instantiates our object or calls our stateless functional component and caches that result. And it does this. So we don't have a complete picture of the DOM until it recursively descends all the components that are in the tree and does this for everything in the tree. So this is how React manages all the lifecycle applications that it's going to call as well, right? There's a constructor, there's component will mount, there's component should update, there's render. So React has a cached instance of our component class that it can call all of those lifecycle functions on as the rendering process takes place. So reconciliation is the process by which the element tree that we've built gets turned into the DOM that's presented to the user. So the problem that it's solving is called graph edit distance, and it is the generic graph edit distance algorithm is an n-cubed algorithm, which for any reasonable sized component tree would be far too slow to run in the browser. So React does a bunch of shortcuts that just make it a single pass through the tree, just linear in the number of nodes that are in the tree. And many of the best practices that come out that are described for building React components come from that, the way that reconciliation takes place. So let's say a render call has generated an element tree, and it's got a change in the DOM node. So reconciliation is now going to take place. So we've got our element tree, we've got our cache of the React state of the world, and then we have our actual browser DOM that is the elements that are presented to the user. So React comes in and it starts looking at the two things on the left. Div, good, we're doing good. Header, good. So it looks at each element down from the root of the tree on down, and then it recursively looks at each child and determines whether that child needs to be replaced. So image, all right, we're doing great. Then pdiv, well, we have a change to the DOM here. So we're going to need to make a change. So React makes a change to its internal state, and then it starts building an edit list of things that are going to be changed in the DOM. So when we execute this in the DOM, we're going to delete div, and we're going to add p. Keep going down the tree. We're going to add an edit, and then we're going to add the rest of this stuff too. So we've got our element tree, we've got our internal representation, and we have our DOM and an edit list. Then the final step, React is going to commit all these changes and execute all these edits against the DOM. At which point, the browser paints, the render is complete, the element tree is discarded, and the DOM now represents what our render call proposed to show to the user. So what made happy squares a slow application? If you look at this process, no matter what happens in the render process, if you end up with an element tree that looks like the things that are in the DOM, there's very little work to do in this middle part where you're going through React's representation. So no matter how I try to manipulate the calls of the render, what came out of the render was an element tree that always looked exactly like what was there. It was 10,000 little squares, some of which were turned on and some of which were turned off. So I mentioned there was one de-optimization I did to really ruin the whole application. And that was I wrapped everything in this breaker component. So what it does is it takes a value in, and depending if that value is truthy, it puts the children inside a div. And if the value is falsy, it puts it inside a p. And so if we look at what happens in our rendering, in our reconciliation, as it comes down, it says, oh, there used to be a div here, now we need a p. And I toggled the value of props.value every cycle of the game of life. So every time it would come down, it would throw out its internal representation of the 10,000 nodes, redraw them, and then create an edit list that threw all those nodes out from the DOM and recreated them. So there's a fast version and a slow version of Happy Squares. The fast version doesn't have the breaker in it and has a couple of other optimizations that turned out to make a difference, a very small difference compared to this. And this isn't totally far-fetched. Presented in this form, of course, it's ridiculous. But with the best of intentions, it's entirely possible that sometimes nodes get inserted into the DOM that potentially confuse React about about what is continuing to exist and what is not. So in a case like this, some well-meaning developer might create a little component, and they need something to attach a modal to, or attach some other element that has a positioning value to it, right? So create a component, something happens, and we change the shell around its children. Well, unfortunately, that causes all the children to re-render. So, and then another possibility is that, not something quite this terrible, but React could potentially get confused about the children living under an element. Say under this P we have 3 children, and if we insert a child at the beginning of the list, potentially React might get confused and start throwing away other nodes under that P that we wanted to keep because they have very big and large render trees. So here's my optimized version of Game of Life. As you can see, it takes about 24 or 30 milliseconds to do a render pass through it, and that is creating 10,000 elements, but I put a counter inside the render method of the class that represents each cell within the Game of Life, and we see that only those nodes that actually get changed get rendered. One of the optimizations that made a difference here was implementing component should update and just looking at the props. We only have one thing we care about for this element, which is whether the cell is alive or dead. So having gone through this experiment, if I wanted to try to make an even worse application, one that would perform even more slowly, I would take a different tack. I would not try to build a component that had such a shallow tree, right? I'd build deeper trees. And a situation where you might run into React spending a lot of time optimizing the DOM, reconciling the DOM. Say you had a bunch of squares on the screen, a bunch of different squares on the screen, and they had different things in them, and some of them had memes with cats, and some of them had like your friends have posted their pictures of their kids, and in some of those squares, your friends without kids had posted pictures of food, and then some acquaintances have posted conspiracy theories. If you can imagine a website like that, there are a lot of different elements that are moving around the page, and the React might get confused about where each element needs to live unless you follow some of the recommendations, such as using keys to indicate which elements are the same in different render passes. So one of the things that's kind of cool about the Conways Game of Life is that it's got these incredibly simple rules that can lead to all these different fun things that you can explore and an enormous amount of complexity. About 15 years ago, Stephen Wolfram released a huge book called A New Kind of Science, in which he explored all these ideas about cellular automata and declared it all revolutionary. And in the time since Conway's Game of Life was created, people have implemented actual entire Turing machines within Game of Life and come up with abstractions that allow you to do computation with this as a computation system. But it's also just fun to explore and play with a little bit. I'll post the link of this application on GitHub afterwards, so you can go play with it if you want to. So I guess sort of a final thought. One of my early mentors in software development told me this once: never call a library function that you couldn't write yourself. And I've added an asterisk here, right? This has always been for me a little bit more aspirational than practical. And as computer programmers, the first thing we have to decide is this statement recursive? I want to write some JavaScript. Do I need to know how a JavaScript interpreter works? If I need to know how a JavaScript interpreter works, do I need to know how memory allocation works? If I need to know how memory allocation works, do I need to know how the virtual memory subsystem of the computer works? And so on, down and down and down. So probably not recursive. Then sort of secondly, the second caveat makes this sort of more of a guideline than a rules. There are some areas that are fairly complicated, and I'm not sure I would ever be able to implement them. I'm not sure that I'll ever be able to build a fully standards compliant CSS version 3 rendering engine. That seems pretty complicated to me. But nevertheless, I use it. it's been a useful idea for me to keep in mind and to sort of direct me into where to explore and how to explore software development as I've gone through my career. So thank you all. Happy Squares is up on GitHub if you feel like playing with it or trying to make it slower or faster or playing with the game of life or anything like that. Thank you.